Hi there! In this video, I'm going to be designing a small circuit that's going to help me align a piece of my test gear just a little bit easier. So really, the whole idea of this video is to show you the thought process behind this circuit design. So really, it's going to be a circuit design from concept to working device, and all the little things in the middle that we're going to have to overcome in order to make this circuit work physically and electrically. Alright, let's get right into the design. The circuit that we're going to design and build together today is a peak detection circuit for this semiconductor curve tracer right here. Now the reason that I need a peak detection circuit is because the sweep voltage that this curve tracer puts out is pulsed, either positive going pulses for NPN transistors or negative going pulses for PNP transistors. And I need to keep this box in alignment with this screen. So if I want this screen to read 1 volt per box this way, it's going to top out at 16 volts. Alright, whereas if I wanted this to say top out at 80 volts, it would need to be 5 volts per box, and I would need to keep calibrating this screen. So I'll give you an idea here. When I turn up the sweep voltage here, I'll turn it up. You can see I'm at center screen right now. Right now I'm calibrated for 1 volt per box this way, so that's 8 volts, and that's 16 volts at the end of the screen. Alright, so if I move the sweep voltage up here to, say, 16 volts, I'm now topped out on this screen, yet the device below, the semiconductor curve tracer, will go all the way to 100 volts of sweep voltage. Now, realistically, that's about 95 volts, but the silk screening says to 100 volts down here. So now I would need to recalibrate this screen so that I could condense this so that it would read, in different increments here, so that I could read, say, up to, we'll say 80 volts, which would again make 5 volts per box across here. Alright, and by doing that, I would grab this and turn that down like so, and then of course, it would, be I get much more range out of this. Alright. So by making a peak detection circuit, it allows me to hook a DC voltmeter up to this, and it will convert these pulses into DC voltage, so that way I can use that DC voltmeter that's on the top here, and I'll show you that DC voltmeter right now. That's the DC voltmeter I'm going to use to align this screen. Okay. It'll allow me to use that voltmeter to set this up correctly depending on the voltage range I want to go to. Now you're probably saying to yourself, why not use this oscilloscope on the bottom to do that? Well, this is set up for relatively sensitive measurement, and this is a dual beam oscilloscope, and right now I'm using the bottom gun. There's 2 guns in this CRT, so there's 2 sets of deflection plates. Alright, so when I move this up here, you'll see it kind of cuts the top of the trace off right there. Alright, it kind of looks like a shadow in front of it. Well, right now that beam is going behind some deflection plates and it's getting cut off because this is the bottom gun. So if I switch this to PNP, you'll see that it doesn't get cut off because this is the lower gun. It's not hitting those plates inside there. Alright, so in order to move this around and change all this, that's quite a bit of adjustment just within itself. So doing this with a DC voltmeter would just make this a whole lot more efficient and very, very quick, and I get a very accurate measurement to what's on the screen. Say I'm wanting to test a Zener diode or something like that. So that's what we're going to do next. So already we know that we need to make a peak detection circuit that's going to look at negative going pulses, positive going pulses, and it's going to have to be able to run this voltmeter above. Since we know that we need to design a peak detection circuit, one of the easiest ways to do that is with an op-amp. So we know that we're going to need some op-amps in order to do this. We also know that the voltages that are coming out of this curve tracer are 0 to 100 volt pulses, either going positive or going negative. Now the input of most common op-amps won't deal with 100 volts, so we also know that we're going to have to create some form of a voltage divider. So say we put 100 volts in here, we're going to get 10 volts out here or something like that. So we're going to need to construct something like that, or we're going to damage the input of our op-amps. I also found a little box of VFDs here, which would kind of be a nice little perk to add to this project and make it a little bit more interesting. So I had these given to me from a fella quite a while back. I guess he maybe took some old calculators apart or something. They look to be in relatively good condition, so I'll test some of these out, and we'll put a few of these things in there, and we'll talk a little bit about VFDs. And then when I get that all put together, I'd like to somehow get those VFDs maybe into a meter face like this. So, have a couple of them maybe hiding inside would be kind of neat. remove the meter and have the VFDs back inside here. Kind of look cool for the project. And when it's all said and done, I'll end up putting the meter into a project box or something like this. Maybe drill a hole here and put it in here, and then at the bottom of the box have some BNCs where it goes to the scope and to the curve tracer, and maybe out to the voltmeter and so on and so forth. So that's kind of where I'm at right now. So I'm just kind of trying to put a plan together and kind of find out which direction I'm going to go into. I got to figure out what kind of op amps I want to use. I have lots of op amps. Since I'm going to try and make this small and fit inside of this meter right here, I'm going to probably end up going with a surface mount op amp. So I'm going to have to choose something from that I have, and the appropriate surface mount components that will be surrounding it. So, if I'm going to be fitting these things inside here like this, I'm going to have to make some pretty good measurements, because, I imagine I'd probably get 3 of them in here. So maybe say something like NPN on them or something, or PNP or something like that. When I switch modes would be kind of a neat idea for this. So, of course, when I'm doing the videos here and stuff like that, that will be on display. So when I'm testing an NPN transistor, it will clearly say NPN. Or PNP or whatever. So I'll figure out what to put on these displays. And another thing is that I really don't want to be controlling these with any kind of a microcontroller, so we're going to be keeping this as simple as possible. So I'd like it to display a whole bunch of things, but keep the circuit relatively simple and small. So I got a whole bunch of ideas going on here, so when I figure out the next step, I'll be back. This is the circuit that I've come up with in order to drive these 3 little VFDs, and it really is quite a simple little circuit. There is no processing or any kind of microcontroller involved in this. All there is 5 SOT23 packaged diodes and 1 transistor, and I get NPN, I get PNP, I get my dashes, and I also get 3 letter A's for alternating. And I'll explain exactly how that works. So we can see here that we have a whole bunch of segments here that are tied together in each one of these digits. Alright, so in this 7-segment display, I have the E, the F, the A, and the B tied together, and the same with this, and the same with this. That's going to be common between NPN, PNP, and the A. The dashes will be a little bit different, and that's on a different line here, and I'll show you that in just a moment. So what happens here is, if I put a positive on the NPN here, what it's going to do is it's going to go through this diode and feed all of these green lines here so that all these digits are going to light up. It's going to be common between the NPN, the PNP, and the A. It will also go down this, light up this digit, so I have an N, because this, and this will be lit. It'll go down this line through this diode, and this digit will light up, so it'll go P, and it'll also go down through here, and we get another N. Alright, now if I feed positive to the PNP line, it will also go through this diode up here, light up these digits here connected by the green lines. It'll also go through this diode, light up this digit to make P, go through this diode to light up an N, and go through this diode here to light up this digit to make another P. So we get PNP out of it, and it's just that simple. So we have NPN and PNP just through a bunch of diodes right now. Alright, now in order to create the dashes, now the dashes appear when there is no signal available. So when there is no transistor in the device, or when I have the sweep voltage down to the minimum, this will not detect anything. This is going to automatically switch from PNP to NPN, and it will detect which one I'm in automatically all through just that one cable. So when there is no signal present, the dashes will appear. It'll be this one, and this one. And how that works is, there always is a positive voltage on this 10K resistor. Now, vacuum fluorescent displays are relatively high impedance devices, okay? So this 10K resistor here is not going to really matter much. It's not going to even look at that 10K resistor. The only reason this 10K resistor is here is so when this transistor pulls to ground, it does not short out the positive supply and of course burn the transistor out, turn it into a jumper, and then destroy my power supply. So there's a positive here all the time, and the dashes are lit. So when there's no signal, all of this dash, and this dash are lit. As soon as I apply a positive signal to the NPN here, what's going to happen is the voltage is going to go up through here and turn this transistor on and drag this towards ground, bringing those dashes out so it doesn't, confuse the display, and we get our proper NPN or PNP, same thing. You can see they're both tied this way. So really, this here is a blanking circuit for those dashes. So when I get an NPN signal, the blanker turns on and the power doesn't get applied to those dashes anymore through these diodes. Now it is getting applied either through the NPN or the PNP channel here, either or. Now when the signal is removed from here, what happens is this deblanks and then the voltage is back on here and it lights up the dashes again. So now we have NPN, we have PNP, we have a blank. Now in order to get the letter A for alternating, which means that it's sensing a positive peak and a negative peak, what happens is if both the NPN and the PNP line go positive, we get the letter A. That's how that works, because these segments are lit, this segment is lit, and this segment is lit, giving us an A, an A, and an A, indicating that we have alternating present. Now, the unit itself doesn't produce any any kind of alternating current or AC voltage whatsoever. The display is only either positive or negative, but if I have a loose connection, it will show a letter A and tell me that, okay, something's wrong here, it's missing a ground or something like that, because it's just going to pick up noise and it's going to cause alternating. Kind of like in your scope, when you grab the positive lead, you'll see an alternating signal on there. It's just you acting as kind of a random hum antenna. Same kind of thing with this. If we have any kind of loose connector, it'll just display the letter A. Or if I wanted to use this for a different application down the road, it will also it'll work for that as well. So just with a bunch of diodes and a transistor, we get PNP, NPN, dashes, and the letter A. Now how the actual tube works itself, I'll briefly touch on this. The tube itself runs the same way as a triode. Okay, so we have the filament, a grid, and we have these segments acting as the plates in the tube. So these technically are little glowing, I guess you could almost call them targets. So what happens is when the filament's hot in any kind of vacuum tube, it emits electrons, and the plate, if it's positively charged, it will attract those electrons. So the electrons will fly off the filament inside this tube and strike these parts of the digit. When it strikes these parts of the digit, it illuminates that portion of the digit. And that's really how that works. Now the grid is a controlling aperture inside of this tube, and by applying a negative voltage to the grid, basically it stops the electron flow and it can cause a dimming effect. So what you can use this grid for is either blanking or dimming of the digits. When they're using these things in an array and they are multiplexed or anything like that, the grid can be kind of a handy thing to have. Or if you want to use it for a brightness control like what I'm doing, absolutely fine with that application as well. So really what's happening is I'm variating the grid from basically ground up to the supply voltage for the targets here, and that's allowing me to dim and brighten these. Now depending on the supply voltage, you don't want to have your targets too incredibly bright. You don't want to overdo it, because you'll cause burn-in on those little the little fluorescent targets inside there. Okay, so you want to make sure that you current limit that, or just make sure that your brightness range isn't too high. If you have like a 50-volt power supply and you're running this, you're going to need to run some current limiting or keep the voltage very low. This is running 30 volts from cathode potential to the actual plate. So 30 volts is enough to get quite a bit of brightness out of these VFDs. In fact, as much as I would want to see out of them. So it's very simple to test a VFD. If you have a VFD and you want to test it out, tie the grid to the plates or to the little segments here, or just give the grid the positive voltage that you're going to apply on these, which is usually, you can tie a bunch of 9-volt batteries together and just test it out with a bunch of 9-volt batteries. The filament is usually around a volt or under a volt. If you put 1.5 volts on it, you're going to kind of be stressing it out. These VFDs here, there's kind of a trick to powering these things up. There really is no specs I can find online for these little VFDs whatsoever. I have a pinout, and that's all I could find. So the rule of thumb with a VFD is you get the filament bright enough so that it's going to cause the targets to light up correctly. Now in my case here, I can't even see the glowing of the filament. It's that dim. A lot of companies that run VFDs will overpower the filaments and they'll put a blue filter in front of it so you don't see the little orange glow of the filament string. Like these VFDs have a filament string that run right in front of the digits. All right, and that's the cathode for the whole digit. Now, what I do in order to, save VFD life whenever I'm working with a VFD or anything like that is I give it just enough filament voltage until the digit lights up and there is no crawling on the fluorescent digit. You'll notice that if you power the filament up slowly and you have these, powered up, you'll notice that there'll be a little bit of crawling on one of the digits if you light up an 8. You'll notice that when you get the filament to a certain brightness, the crawling will stop. All right, what I do is I give it just a little bit more voltage than that, and the VFDs are stable thereafter. A lot of automotive manufacturers and a lot of microwave ovens that you see, and like the old DVD players and stuff like that, they have VFDs in them, and they are glowing orange across the whole screen. That's a little bit too much, and of course that limits the life of the VFD. So again, you want to give it just enough filament voltage so that electrons are coming out of this thing, and that you're not burning the filament out. And of course, if you're going to have them displayed like I am, I don't want a visibly orange glowing line right through the center of my VFD. So again, this I think was around comfortably 0.8, 0.9 of a volt for these VFDs, and that caused them to glow absolutely fine. Thereafter, the brighter you make the filament, it doesn't really change any of the luminance in the fluorescent targets whatsoever. Again, just take it to the point to where you stop crawling. Once you see the filament start to glow a little bit orange, you're pretty much at its max. It's not supposed to glow any more than that. If you're glowing them like light bulbs, you're going to burn your VFD out just like that. They're not designed to do that at all. Again, so this here is in my tubes. You'll notice that when I show you this later on in the video, you'll see that the actual VFDs themselves, you can't really even see the filament glowing whatsoever. So that's really how a VFD works, and you make a VFD tester really with a 1 volt or a 1.5 volt AA or AAA battery and a couple of 9 volt batteries, and you could plug your VFDs into them all day long and test them out if you'd like. So remember, again, the voltage, the 1.5 volts, you would want to put a little potentiometer or something on that so that you could vary the filament voltage. Always start with it off and slowly turn it on, so that way, because if you don't know the specs of your filament, that could be the breaking point of your VFD. You could ruin a VFD just like that. So that's how these work. So what I've got here is I've got just a BC817 and a 100K resistor, 10K resistor, variable resistor with a 2.2K resistor to ground, and that is my brightness control. So what I'm doing is I'm just basically turning this transistor on and off, using this as a pass element, like running it in the linear region. And these grids, they pull basically no current whatsoever, very, very low. I think all 3 of the grids in this maybe pull a milliamp and a bit, or a little over that. Very, very low current. The grid inside of a vacuum tube is very much like the gate on a FET. All right, the vacuum tubes are voltage controlled devices, where transistors are current controlled devices. All right. And that pretty much explains this. So what I'll do now is I'll go into the actual schematic that's going to control this. I'll get rid of all this stuff here, and I'll show you my little op-amp circuit that I've come up with to make everything kind of jive and work together. This is the circuit that I've come up with in order to drive those 3 little VFD tubes and also to make a DC voltmeter read from my curve tracer. So I'll explain this circuit here. There's a lot of op-amps in here, and I really don't want to get into op-amp theory at this time because, that's an entire video within itself. But I'll go through the sections and just, kind of do an overview of exactly how everything works here. So this is the input here. We have the input is, again, 0 to 100 volts. The input of the op-amp won't like that. So I have a 910K resistor here and a 100K resistor here. Now 910 is as close as I could find that I have in one resistor package to basically take 100 volts at this point and turn it into 10 volts at this point. A true value for this would be 900K and 100K, and then that would be a perfect divider for 10 volts at that point. So I took a bunch of these resistors and graded them, and I got one that's relatively close to 900 just by sorting through a whole bunch of resistors and grading them on the ESI. But at any rate, this is we'll call it 910 because that's what it originally was. So 910 and 100K. So we're going to say that we have this down at 10 volts here. Say we have 100 volts coming in here. We have 10 volts in here. All right, these are buffers here. This is the section here that is going to drive my digital multimeter, all right, and this here is basically just a switch for the NPN, PNP, A, and the dashes, and I'll get into that after I explain this here. So this is just a voltage follower or a buffer here, so basically just, you know, trying to keep the loading off this particular area and keep it as accurate as possible. This section here is a switch which keeps the voltages positive no matter if I go to PNP or NPN. So say I go to negative 60 volts at this point here, all right, the voltage here will be positive 6 volts. If I go to positive 60 volts at this point here, the voltage will be positive 6 volts here again. So all this is doing is this is just keeping everything positive. So if we were to ignore this, this is basically unity gain or very close to unity gain. So we'll just consider it as being that. If I put positive 1 volt here, I will get positive 1 volt here. If I put negative 1 volt here, I will get positive 1 volt here. If I put negative 5 volts at this point, I will get positive 5 volts at this point. If I put positive 5 volts at this point, I will get positive 5 volts at this point. And that's really how this is working. It's just keeping it positive. And the reason I want to do that is because at the end here, I have a peak detection circuit. And in order for me to have two separate peak detectors, one for the negative and one for the positive, would require more switching. So this little circuit here is automatically doing that, and it makes things quite a bit nicer, so I don't have to have, you know, more complex circuit. Each op amp I'm using has 4 inside it, and it just happens that I can use all 4 up. Now, this is a TL074 on the top. I found that that works very well for this application, and I have an OP484 on the bottom for this section here, and I'll get into explaining this in just a moment. So really what's happening here, again, 100 volts here, 10 volts here, so we'll have positive 10 volts here, and then this is just a peak detection circuit in the end. So what this is going to do is this capacitor and this resistor here is going to hold a nice peak value, so I get a nice accurate reading on my DC meter. So basically it's going to turn that pulsing into just, you know, a nice clean DC. It's going to be detecting the peaks. And that's really how this little section here works. These here are trimmers for the NPN and the PNP, so just correction for the rest of the circuit here. It's very close to unity gain. Again, you know, there's going to be some differences in here and maybe some other resistance differences in here. So this allows me to trim the NPN and the PNP side for, you know, accuracy, very good accuracy. So we'll say that, you know, this 10K resistor really isn't 10K, and this isn't, and you know, there's all sorts of, we have a whole bunch of resistors in here that might have, you know, slightly different values, so I can just trim these up. So these are just a correction for the NPN side, and this is a correction for the PNP side. There's a little bit of interlock between the two, but very, very little, and not enough that it's going to cause any issues with an alignment. Down on the bottom here, it runs into these 2 op amps here, which again are just voltage followers acting as buffers to isolate the circuit. And what happens is we have 2 paths here. This is the NPN side, so this really is non-inverting, and this side here is inverting. So what's going to happen is when I have a positive, say 400 millivolt signal in here, all right, if 400 millivolt goes into here, I'm going to have 40 millivolts at this point. We have a gain of roughly around 100, so I'm going to have, around 4 volts, say for argument's sake, at this point here. And that's really about the time that, you know, through these 2 4.7K resistors, I have a voltage divider again, and that's when it turns on these optos, and I get a nice clean, you know, transition to on and off. I really don't have that like a dimming effect in there. If I really try and play with the sweep voltage control on there, I can kind of get it to go between the dashes and then lighting the NPN. But for most of, you know, like you're not going to be doing that. You're just going to be zipping past that. And to get this to go to 400 millivolts is you're just breathing on the sweep voltage control. It's, you know, you just touch it and it goes up there right now. So it's really designed to, you know, be in the volts, I imagine. 600 millivolts or 0.6 of a volt is, you know, the standard for a normal diode if you're going to look at a diode at its forward. So at any rate, so that's basically how this channel's working, and this is the opposite. This is inverting. So what's happening is when we switch to PNP, this side here won't be activated anymore, but this side will, because this is inverting, and now this is looking at the negative side, and it will turn this one on much the same as this. So they really come in very close to the same The gain is very close for these ones. It's around -100 for this particular section here. Of course, we have diodes and stuff in here, so we're just going to generalize. This section here, there was no real, you know, I guess you could say super planning in the gain. You know, basically 10K and 1 meg is what I found to work very, very well in this. Basically what I want this to do is at signs of very low voltage just to turn on. Really, that's all I'm looking for. And I found that 10K and 1 meg is nice and stable. I'm not having any issues with anything. You know, if I go too incredibly high on the values here, I might get instability in this circuit, and I really don't want that. So this is nice and stable. And, you know, 400 millivolts, it actually comes at just a hair earlier than 400. Is absolutely fine. Again, the standard diode or, you know, standard transistor is around 0.6. The monitor that I have really comes in at about, with the blanking on it, about 1 or 2 volts of input. So, you know, the first 2 squares, if I'm using the full screen from 0 to 16 volts, you know, it takes the first 2 squares before you actually see the line on the bottom, the sweet voltage line. So that's really how this thing works. That's, you know, that in a nutshell. This runs off to the NPN line on that other drawing that I had previous to this one, and this one runs off to the PNP line, and that's just really how simple it is. So you put an NPN transistor in there, or have the switch set to NPN. This side is going to activate and turn on and make it say NPN. If we have a PNP, it's going to turn on this side, PNP. If we have an AC signal, of course the AC signal is doing this, so it's going to be turning these on like this. Now we have 2 capacitors here, which of course keeps these both kind of glowing, the LEDs inside these optos glowing, and by having those optos glowing, we get the letter A for alternating. Now the reason that I'm using optos in here is because the circuit that runs with the VFDs is running rail to rail. So basically the negative for that whole circuit is the minus 13.3 volts, and the positive for that is the positive 13.3 volts there. So we're going all to the actual VFDs, we're going all the way from negative 13.3 to positive 13.3. So in the VFD circuit, this is ground, not this. So by having these optos here, I can successfully isolate this entire section from that and then use this as the ground for the VFDs instead of having the ground in the center here. And that's really why I'm running the optos in here, basically kind of like a, you know, a level adjustment in there. If I was using just a normal 7-segment display, you know, an LED type display, I wouldn't need all this kind of stuff. I could just, you know, do it without all that. But again, it takes a little bit more voltage to operate a VFD, and this is the easiest, how would you say, adapting for the 2 separate voltage levels, I guess you could look at it like that. And that's this circuit. So next we'll go to the computer. I'll put this on a small circuit board, and we'll take a look at the circuit board, and then I'll populate it, and we'll go from there. This is the little circuit board layout that I've come up with here, and when I say little, that's the actual size of the board right there. So when I put my thumb on the screen, you can see that. You see I'm pressing my thumb on the screen. It's actually just a little bit smaller than this. The screen, when you start to build things on the screen, it does decalibrate just a little bit. It's accurate enough so that if I, you know, have a component and I lay it on the screen, it will be the same size. But when you start to build and start to add on to things, it does start to decalibrate just a little bit. But very close at any rate. So what I'll do is I'll just magnify this here, and we can look at this a little bit, you know, a little bit closer. So the green layer is the top side, and this brown layer that you see here is the bottom side. And you'll see that these red dots are all over the place here. Those are drillable pads. So this is a connector up here. And these here are 2 opto isolators. These are actually through-hole parts because I didn't have any surface mount optos. And this layout here is for the VFDs, the 3 VFDs. And so on and so forth. So what I'll do is, just to make this a little less confusing, I'll get rid of one layer. I'll get rid of the bottom layer here. And this is just the top side of the circuit board. So we can see this is where the OP484 will mount. These are some tantalum capacitors here. These little parts here that you see are all 04, 02 parts, and they're pretty small, so I usually mount those first before I solder anything else. And then what I'll do is I'll put on these SOT23 package diodes. These are the diodes that do the switching from NPN to PNP and the dash and the A. Alright, so I'll mount these first on the board, and then I'll probably install the center VFD first, and then I'll go to the two outer sides. Now, I'm soldering the VFDs in, and I'm imagining that the legs of these are going to be pretty close to the board. I still have to do some final measurements. It looks like I do have clearance, so I'll be fine. But whenever you're soldering anything so close to a glass seal, you know, there's either Dumit or Kovar on that glass seal there, and you got to be very careful that you don't crack the glass, so you want to keep the dwell time of your soldering iron as short as possible whenever you're soldering anything onto pads that's very close to a glass seal. So I'll have to put these in. I'll put this one in first, and I'll have to solder all these little dots. Now that's going to be some pretty fine soldering. Again, if we go down to the size, that's the size of the area, and I have to get my soldering iron in between the little wires that are going to come out of the bottom of the tube. So, and then I'll put in the two end ones, and then I'll just solder some of the larger components. Keep in mind that these are vias, but there is no through-hole plating in these boards, so you have to use a piece of wire for that. Whenever I use a through-hole component like this, it's kind of a bonus because the leads go through the circuit board and you just solder both sides, and you get your plated via, i.e. the pin of the IC. So that makes things pretty handy. I try and keep my via count down. Here's a via down here. There's 3 little vias here and 1 via up here. And you know, that's no problems. I usually use Kynar wire in order to put them through these little via holes, and that works very well. Now the IC is a surface mount IC, and it will probably fit very close to being flush to the circuit board, so when I put this through, that Kynar wire is very small, and I'll solder this as flat as possible. And sometimes I'll even clip the top of the solder ball off, and then that way when I put the IC on the top of the board, it will sit flush with the board and it won't interfere with the height of the surface mount component. Right here is a VR. This VR adjusts this pass element right here, which is a BC817, which controls the grid of all 3 of these VFDs, so I can control the brightness of these VFDs. This is where a 1K resistor sits across, and this is for the filament line on the VFDs. Now, all the filaments of these VFDs are in series, and that's taken care of on the bottom side. Since they're in series, this VFD here is going to be the highest from being at actual ground. So this one will be maybe a volt or 2 above actual ground. So if you were to say put 6 of these in a line, the farthest VFD would be a little dimmer than the first one. So it's a good idea when you're using these kind of VFDs to only run 3 in series and then start another 3 in series and do it in that fashion. Either that or you're going to have a brightness difference, because the higher you get the cathode potential from ground, you know, the dimmer the VFD is going to be, because technically you're putting bias on the tube at that point. So you want to keep them as close. So 3 is a good number to stick with, and works quite well. This is a 1K 2-watt resistor up here. I was contemplating using a pass element in order to control the you know, the filament voltage of the VFDs with a VR. But that's touchy ground. If that pass element ever shorts, it'll just burn all 3 of these filaments out in, you know, in the blink of an eye, and I don't want to do that. The failure mode for resistors almost always is open, so I don't really have to worry about that. I'll never, you know, have anything go wrong with the filaments in these VFDs. That's a very sensitive part of the VFD. Any over voltage and you know, they're gone immediately. So other than that, that's this side here. This is the entire top side of the circuit board is just dedicated to controlling the VFDs themselves. Now, if we go to the bottom layer, this side is for peak detection and you know, basically just some, you know, through bridges, you know, via some vias really. If you remember on the whiteboard, we had a bunch of green lines that were connecting a whole bunch of the internal segments of the 7-segment display. That's what this line is here. That's just, you know, bringing those all together. You'll see that down here is a via, and this here is one of the grid vias. You can see the grid is pin number 6, and that joins to here, and that will attach to pin number 6 over here and run up to that VR on the other side. This here is a TL074 op amp right here. These are just a bunch of supply line vias, and then we have one running with some signal here. This is that 910K resistor here, and this is that 100K resistor voltage divider, and you can see it runs right into the input of the IC right here. This is the compensation VRs, both number 1 and number 2. So number 1 is the NPN compensation, number 2 is the PNP compensation. Now, whenever you're making a circuit board here, just a quick tip once again on circuit boards, the top layer at the printing process is always mirrored. The bottom layer is not mirrored. You don't mirror the bottom layer on the printout, but the trick is any printing that you do put on the bottom layer has to be mirrored. So that's where it gets confusing. Believe me, if you do this a few times and you get the layout backwards or wrong, you'll start to remember very quickly. So it's a real pain to lay these out more than once. You have to, take acetone or something and take all the toner off, and then re-clean the board and do it all over again, and make sure that you don't get any mistakes. So I've been doing this for years and years and years, and it just comes naturally now. But if you're just starting to fool with any kind of a layout program, if you get that wrong a couple times, you'll learn pretty quick. It's a real pain. So this is the bottom side of the optos. The optos are on the top side. What else can I tell you here? That's pretty much it. The filament line here, this is pin 1 and pin 7 are the filaments, so 1 is ground, and this is the ground via here. So you can see they're in series 1 to 7, and then 7 to 1, and then 7 to 1, and then 7 runs out and goes up to this resistor here, and this is the resistor in line. So this one here is the furthest one from ground, but the brightness still remains, it's unnoticeably different. So again, if you had 6 of them or so and you wanted to run 6 of them in series, you would start to see a difference by number 6. So rule of thumb, VFDs, only about 3 of them in series would be about the max that I'd do. Now you could run these on AC if you want, but you'll get a visual flicker as the as you're dealing with the alternating current on the filaments there. Of course, as it crosses 0, you're kind of getting a pulse. So the reason that I didn't opt to use AC on here is because I do have a 5-pin connector, and I want to keep the pin count down, and I also don't want to run any AC wires into this connector. You have to remember that we're dealing with a very sensitive input signal here. 40 millivolts of signal is going to cause this to either go to PNP or NPN, and that's even giving. It's probably more around 30 or so like that realistically. So a very, very slight signal on the input here will cause it to change. If I touch the input here with just my finger, even through the voltage divider, this will indicate A for alternating. That's how sensitive this is. So I want to keep all the voltages on this connector even. And the way that that works is this connector here is the input. As you can see, it goes through that voltage divider. This here is the positive. So this is the positive rail. Number 3 here is just ground. Number 4 is out. So this is where the signal comes out of the board and would go off to my DC meter. And number 5 here is the negative rail. So this is how this works here, and there's a V in the negative rail to take it onto the other side of the board there. And that's really how the layout works. So again, looking at this at normal size, I do have a little bit of soldering to do, and it is going to be pretty small. So next, what we're going to do is I'll just show you the power supply, and I'll get on to building the boards. This is the power supply circuit board that I've come up with for this little VFD project. Again, this is much bigger than it really is. F3, that's the real size there, so you can get an idea of the real size. Remember, I have to fit this inside that black project box, so it has to be relatively small. So I'll just make it big, and we'll take a quick look at it. This is where the power transformer mounts. The little power transformer will sit right on the board. This here is a bridge rectifier. These are the filter caps. This is the connector that runs off to the VFD board. This here is the connector that runs into this board. So basically there's a signal in, a signal out, and a ground at that connector there. These large pads here I will drill, and they will be basically mounts with standoffs to hold the board up. These little marks you see here on the corners, those little kind of brown marks on each corner, are just guides for when I cut this off of the main sheet of printed circuit board. So what I do is I usually draw a line that's just a little bit above it and cut it in my bandsaw, and then I plane it down to this layer here, and I get a nice square circuit board that way. These are the AC supply lines in, and again the AC out that runs into there. So keep in mind, again, we're looking at the circuit board through the top layer. There is no top layer, so we're looking at the bottom layer. Again, when you print this off on your laser printer or anything like that, whenever you're printing the bottom layer, you do not mirror the print, but you do mirror any of the lettering that you do put on here. It has to be mirrored or it will be backwards. So that is the bottom side of the board. So what I'll do now is I'll populate both the VFD board there, and I'll populate this power supply board, and I'll be back and we'll take a look at them. Before I go populating the circuit board, what I do is I print off the actual layer on a piece of paper and mark in all the component values, so that way when I am populating the board, it makes it quite a bit easier to have this beside the actual piece I'm populating. I also put this in a file, and if a year down the road, if I wanted to build another one or add to this or use something from this idea, it's all there. So this is the power supply here, and this is the VFD board right here. You can see I use lighter colors so that I can print in them with a pencil or whatever, and it shows up on the lighter color. Black and green is really nice to use on the actual computer screen. It's comfortable on the eyes, but when it comes to printing things off and marking in component values, lighter colors work quite a bit nicer. So you can see the back side here is kind of like a sandy brown color, and that works. You can see the actual printing when I write in the ink from the printer. Now the factory default values for that program are red and blue, and looking at that for a long time can really give headaches. So I've changed the color, and it works quite a bit nicer like that. So let's take a look at the power supply. This here is the power supply that I've put together. Nice little handy transformer. I have a few of these around. The filter capacitors right here and the bridge rectifier down in the middle. This here is the lead-in wire that goes to the VFD, and this here is where the signal comes in and out, and a ground. So relatively simple. The back side of the circuit board right here is, I don't know if you can, the light glares on the traces, you can get an idea of how the traces look. I'll zoom in just a little bit. So that's the back side of the board. I'll move it around in the light there. These are tinned, so the actual tin traces sometimes reflect light and look a little bit odd, so I'll just move it around. So I didn't have an actual pad layout for this transformer, again, just like the VFD, so what I did is I just made one. It takes a little bit of time. You got to get a caliper out and measure between the pins and stuff like that, but in the end, now I have a saved pad, an actual layout for this, and I have a few more of these transformers, so it does pay off down the road. But everything else is pretty standard. The connector is a single inline pin 5 connector and 3 and stuff like that. So that worked out very well. You can see this is where the standoffs are going to go. And I also have a line cord on this. I'm ready to try this out. So we'll check this out in just a moment and see if all of this work pays off. This here is the VFD little display. This is the top side of the board. You can see the little SOT23 package diodes down there. You can see how tight the pitch is between the pins there, so soldering that is a lot of fun. Going on to this side here, we can see that this is the two optos here. Again, still the top side. This is the resistor for the filaments here. This little VR that you see right here, that VR is for the brightness. And yeah, just everything else that's associated on the top, the resistors and the little 0402 parts that are, right down in the bottom there. This is the bottom side here. And these are the two correction VRs in the center. This is a TL074 right here. And just associated components again, the tantalum capacitors, and everything's been soldered on both sides, as you can see. Again, the pins of the actual tube are the vias. Now you can see how close the actual tube is to the circuit board itself. So again, the dwell time of the soldering iron, whenever you're working this close to a little glass case, you can see those little, they look like little red pins inside there. That's the sealing on the tube where the pin goes into the actual vacuum tube. You don't want to create any problems with those little red seals in there. It's either Dumet or Kovar on the bottom of these tubes. So again, the dwell time of the soldering iron has to be relatively short. So that's the little VFD board right there. So next, let's put power to this and see if it works. All right, the moment of truth has arrived. I'm pretty sure that this is going to work just because I've quadruple checked everything I've done, and I'm pretty good for that. When you build a little circuit board like this and you spend this amount of time populating it and making sure everything is right, you definitely don't want to have any issues. So this is correct to my schematic, and if the schematic is correct, this should be absolutely fine, and I'm pretty sure that everything is okay there. There's a lot of work in just putting this thing together, getting the VFDs all perfectly straight up and down so that they're not side to side, and making sure that, you know, they have even spacing between them, and everything is quite a bit of work just doing that, and you have to pretty much tack 2 little pins of the VFD and move them all around until they're perfect. So the middle one had to be perfectly centered, and then the outer 2 were pretty much just aligning with the center one. You know, quite a bit of work there. Again, you know, removing these VFDs after they've been soldered into this board would pretty much be the end of them. So lots of checking at this point. I have this on a piece of cloth right now because if this tips over, I don't want the VFDs to tap the bench. They are very fragile, and you don't want to have any issues. The actual cord here does have some twisting in it, and I don't want it to pop over. Now, if you're ever doing any experimenting with a new circuit board or a new circuit, unless you're pretty confident in what you're doing, I really don't suggest that you test something on a piece of cloth, because if one of these tantalums were to go away on the bottom, we all know what tantalums do when they go away, and that wouldn't be so good to have that on a piece of cloth. Again, I've quadruple checked everything, and everything is orientated correctly on the bottom here, so those tantalums are the right way. So even if there was supposedly some issue with the board, at least the tantalums should be fine. And of course, I'm standing right here. Alright, so I have to plug this thing in. I've got my meter hooked up so I can see if the peak reading side is working as well. And I'm going to have to turn on my curve tracer. That's all turned on with one very large master button there. So I'll reach behind here and plug this thing in and keep a close eye on this. It should start with dashes. And there they are. Now, the reason that you see the dashes come on slowly is because these are vacuum tubes, and that little filament that's in front of the tube here that you really can't see because it's barely glowing has to warm up in order for electrons to flow, and that's why you saw those dashes come in rather slow. Now, if you're used to playing with electron tubes and stuff like that, you'll notice that some tubes take quite a bit longer to come on. These would be considered a directly heated tube, not an indirectly heated tube, and that's why they came on pretty much right away. So what I'm going to do now is turn on my curve tracer. I'm going to reach over here, and there's one big master switch. Turns on everything. Alright, now the curve tracer is on, and it is set to PNP, it looks like. Okay, so what I'm going to do is turn up the sweep voltage control, and a PNP should appear on this display. So here I go. I'll turn it up, and there it is. Now I'll turn it back down again. It's off now. Working good. Turn it back up a little bit again, and it's right back in. I kind of like that delay in there. That's done by those capacitors on the bottom. That's also what contributes to that letter A. So I'll turn it off. You'll see how slowly it'll blend back to the dashes. I'll turn it off right now. So it's kind of a nice slow blend back into the dashes. So I'll move the switch over, and now it should say NPN. So I'll turn it up. And there we go, we're testing NPN. Turn it down again. Turn it up again. And turn it down again. Now I'll pull the jack out of the curve tracer. And when I touch this with my finger, I should get the letter A, because this is sensitive enough to pick up my, just the 60 cycles in my body here. So this is what's plugged into the top of my curve tracer, and I'll just touch this and I'll impose some alternating current into this. So it should say the letter A for alternating. And there it is. So everything is working correctly, at least on this side. So now I need to check the peak detecting side of it. And really what I need to do is turn on an oscilloscope and hook a scope up to the leads that come out of the curve tracer, which are attached right back here. And then I need to calibrate this little board on the bottom side so that the DC voltmeter matches the peak voltage on my oscilloscope. And that requires, you know, more than two hands, really. I can't really control the camera and do all that at once. So what I'll do is I'll get all that out of the way, and I'll start putting this thing into the project box. And of course, this thing is going to go into that little meter that I still have sitting on the bench here. So it's going to go into this little meter face here. And get that all out of the way, and when I have some more to show, I'll be right back. I managed to get everything hooked up. I had to pre-align this just because it's just too much to do on camera right now. But I have my oscilloscope hooked up to the output of my curve tracer, alright, just above here. And this is hooked to the output of this, so this is reading the peak voltage right now in volts DC. So you can see right now, I'll just move this down. It says NPN on the bottom. This is taking all of my wide angle lens to do this in such close quarters. Now if you look right over in this corner right here, that's the peak to peak voltage. So you can see we're at 100, it's flashing 100, 100.1, 100, 100.5 really. So with this you have to move the decimal over, right? Because remember this is by 10. So you got to move over one decimal place. So this is 100 volts, right? Alright, so what I'll do now is I will turn this down. And now it shows we have 64, maybe, yeah, 64 and a half, not touching 65. And you can see we have 64 down here and 64 up here. So the peak-to-peak detector is working, or peak detector. So I'll turn this down really low. Let's hit auto set here. It's easier than getting in there and fiddling with things. And it says we have 33.4, 33.3 volts, and here we go, 33.25. So absolutely fine, working just great. And that's exactly what I want to see. So what I'm going to do is on my Nixie meter up top, I'm going to take that decimal and just move that decimal place over so that way it's less confusing. I'll probably put that decimal place just on a switch on the back or something like that. That meter is going to be solely dedicated to this. So yeah, that'll work absolutely fine. So just bump the decimal place over a bit and away I go. So again, I'll turn this right back up here, topping out on the scope. So hit auto set. I have it averaging. And there we are, back to 100, maybe 100.1, 100, right? 100 and a half, a little over 100 and a half, so it's working absolutely fine. And it's the same for the PNP side. So everything on this little VFD display board / peak detector right down here is working absolutely great. Here's a quick look at the digital voltmeter that I'm going to be using to align the boxes or the graticule on the WaveTech monitor. Now, this is a digital voltmeter from the mid-1960s, and you'll see that the display on this one is orange. It's not blue like the vacuum fluorescent display. Now, they're both tubes. Each one is an individual tube. The 1, the 2, the 3, and the 4 that you see lit there are all individual little neon tubes, and they have the numbers 0 through 9 stacked inside them. And what happens is the digital voltmeter picks a number and grounds it out, and that's what gives us the display. So right now the 1 is grounded, the 2 is grounded, the 3 is grounded, and the other 3 is grounded. And in order for it to switch the digits, it basically lets that one float and goes to the next one and grounds it out. Now, this is before they had high voltage transistors, and when I say high voltage, I mean around 150 or 200 volts even. So what they had to do in order to make these displays work correctly is they had to use a photocell and another little neon bulb. And that little neon bulb that you see on the front there is pretty much exactly the same bulbs that they're using inside this unit, except they're clear. That one's frosted. So these cards have little boxes on them full of these neon bulbs. These are the little boxes that are full of those neon bulbs. They're just stacked in a row inside there in front of photocells. As you can see, the cards in here, there isn't a single IC in this. This is all transistorized. No microchips whatsoever in this. And this is a multifunction meter as well. It does volts, ohms, and amps, but it won't do AC. It only does DC. So back to the display here again. So a lot of these old HP, voltmeters and frequency counters, they didn't use the standard logic that we use now. They, 1, 2, 4, 8, 16, 32, 64, and so on like that. Because they only need to go to 9, they used 1, 2, 2, 4. And that was the logic. So we can get 9 out of those 4 numbers. So there's, if you're ever trying to troubleshoot the logic in one of these old HP units, there's a chance that it is 1, 2, 4, 8, because they did use that as well. And they also used 1, 2, 2, 4 as their logic. So anyways, there's just a quick little overview of this digital voltmeter. The reason that I've got this open again is because I just want to shift that digit. I'm just going to, or the decimal place. I'm just going to take that decimal place and move it over to the next one here. So really, in behind there should probably just be some swapping of wires or something like that. And that should be a relatively quick and easy job. So there you go. That's the difference between a Nixie tube and a vacuum fluorescent display. The project is nearing completion. You can see I've got the meter installed in the plastic box here. I just used a hole saw for that. On the other side of this is the power supply. There are some standoffs on the other side of these screws here. You can see the BNCs that have been installed in the bottom here. On this side here, we can see that 3 BNCs are just paralleled, that's so I don't have to use any external T's, and all the grounds are paralleled all the way across. So these are the inputs here really, and this one here is the output on this side here. There's the power supply, little standoffs, I don't know if you can see that in there. And the little board is installed in the meter shell just with some butyl tape on each side. So it's really quite stuck in there, but if I need to remove it, I can just lift it up and pull it out quite easily. It's pretty versatile tape. Now this is going to be on a slight angle. It'll be facing forward a little bit, so I don't have to worry about this, ever popping out or anything like that. You can see the clearance was really quite tight between the bulbs and the case, but worked out just fine. This is really thin circuit board too. So I'll get the back on this unit here. There's the back with a hole for the line cord in it. And I'll attach it to the WaveTech monitor, and I'll be back. I've got the curve tracer set up, put back together, and I have things situated in this small area here so that it's comfortable for me to use and it works well with the camera. So right now I've got a transistor in the actual curve tracer here, and you can see everything is working well. It's reading the voltages on the screen quite nicely. See at half screen here, half screen is 8 volts. See we have 8 volts there. And at full screen, I've got 16 volts right there. So what I'll do is I'll resituate the camera and remove the transistor here, and we'll just have a baseline, and I'll show you how I recalibrate the screen. I've mounted the project off to the side of the WaveTech monitor here. On each side of the WaveTech monitor there are 4 screws that line the face. I imagine that they intended it to be rack mounted at some time or something like that. So what I've done is I've installed some L brackets under 2 of those screws, and they fasten to the rear side of the project, and it holds the box there really quite nicely. It really is a non-invasive add-on. I can remove the box at any time if I want to switch monitors or do anything like that. On the top of the WaveTech monitor is a Nixie type voltmeter, and there's a BNC input on the rear of that voltmeter that runs to the project here. So the BNC jack on the bottom of this project that's closest to the scope is the output. So the curve tracer on the bottom here runs into the box. The output of the peak detection circuit runs into the rear side of the digital voltmeter so I have a clean DC reading on the actual voltmeter itself. I didn't run any cables on the front here because I just wanted to keep the front looking clean. So the whole idea of this digital voltmeter is to help me align the screen of this WaveTech monitor, and right now I've got it set up so half screen is 8 volts and full screen is 16 volts, so really a volt per box this way. Now if I turn up the curve tracer, I have a transistor in here right now. I can align it doing this, but I do have a staircase present, so I get just a little bit of digit flicker at the end. So if I don't want that, what I do is I just switch over to the empty side on the curve tracer, and I get a baseline, and I can use that baseline to align the actual screen up. You can see I'm at 8 volts center screen and 16 volts, full screen. Now I'm just ever so slightly touching the sweep control knob and it moves it around. So really this setup is much more sensitive than it actually needs to be. So I'm really looking for something like 0.5 of a volt accuracy or something like that. Really, I just have to align this up to the edge of the box, and that's how that works. So if I want to change the scaling, if I wanted to change this to say read from 0 to 80 volts, so center screen would be 40 volts and each box would say be 5 volts for testing a high voltage Zener diode, all I would do is just turn this all the way up to 80 volts and then adjust the gain control here and bring it back down to the edge of this box here at 80 volts. And then when I turn the curve tracer down, it would just end up being at 40 volts half screen. And I would do that using this Nixie meter on the top. That makes things quite a bit quicker. So the project is done and it works very well. I'm quite happy with it. So we have a success. Here's a quick shot of what was involved in getting that intro picture right over here. Here's a quick behind the scenes shot of what's involved in getting those intro pictures. Marie, my other half, is the magic behind the photography in these videos. Now trying to get her on camera to say hi, well, she says that's just not going to happen. Well, hopefully you found something useful in this video, something for your next electronic project build or design. If you enjoy videos like this, please give me a big thumbs up and hang around. There'll be many more just like this in the near future. So until that time, I'll see you then.